Hello everybody, this is Cal with section 6.1, Inner Product, Length, and Orthogonality. Um, those of you who have seen vectors before have probably seen parts of this section before. If this is the first class you've seen vectors in, then this stuff is going to be new to you. I will say, either way, I think we're over the tough stuff at this point. I think that diagonalization in section 5.3 is the roughest thing we're going to do, and chapter 6 is kind of downhill from there. So, let's just go through it. I'm probably not going to go in depth on a lot of this stuff. I'm just going to say what you need to know, what you need to work on. Alright. The book starts by introducing inner product. And inner product, or dot product, is it's defined here as U transpose V, and I would not think of it that way. I would think of it this way: U1V1 plus U2V2 plus up to UNVN. A very computational way to find the product. U transpose V is useful in some proof situations. And that's about it. It's not clear from the get-go what the inner product of two vectors means, and we'll get to that. So, for now, it's some number having to do with those two vectors. Theorem 1 gives some algebraic properties of the dot product. And basically, dot products play nicely with linear combinations is one of the takeaways here. That's fine. Length of a vector is defined right here. The way that you compute length of a vector should not be a shock. You should take note that you can write the length of a vector, the norm of a vector, as, well, its square is the vector dot itself. So the norm of the vector is the square root of v dot v. And that's fine. Take a look at this formula here on how scalar multiplication works with length, with norms. This is something you're going to want to know. And there's an absolute value there, so just be aware. Example 2 lets you play with these ideas. And I'm sorry, I should say this first. The book introduces what's called normalizing a vector, dividing it by its length. And example 2 lets you play with that. Okay, so I think I probably missed something. No, maybe not. Okay. Somewhere in here, and I'm just not seeing where it is offhand, the book introduces the idea of a unit vector, and you should make sure you know what that is. Anyway, this idea of length lets us get at distance between two vectors in Rn. And I'll let you read about how that works. The definition is right here. It's a pretty obvious one. And example 4 lets you play with that idea of distance, as does example 5. Now, at the bottom of this page, 335, we get into a new idea called orthogonality. The definition is here on the next page. Two vectors u and v are orthogonal if their dot product is 0. That is the definition that you need to know, and this is a definition that you need to know. The Pythagorean theorem is an interesting theorem about orthogonal vectors. It is not a definition of orthogonal vectors. You want to think of orthogonality, you want to think of two vectors as being orthogonal if they're at a right angle to each other. So, in a sense, this is not a new concept. Then we get into the idea of an orthogonal complement. You want to think of this as if I have a subspace, W of Rn, then if a vector is orthogonal at a right angle to everything in that subspace, we say it's in the orthogonal complement of W, which is denoted W perp, with a little perpendicular sign in the superscript. Example 6 plays with that a little bit. We get a nice blurb at the bottom here, which you'll prove in the exercises if you care to do them. And Theorem 3 is a maybe not so terribly obvious theorem about how perpendicular spaces, orthogonal complements, work. I would read this section about angles in R2 and R3. This gives us the physical interpretation of a dot product, which is kind of useful, and I will be talking about this in class given enough time. So, that's about all we've got for 6.1.